Hello everyone, welcome back to my general chemistry mini lecture. We will talk about the Lewis structures of the molecules and ions. There's a lot of steps to draw the Lewis structure. First step, you need to determine the total number of valence electrons. And make sure you add electrons for anion, subtract the electrons for cation. So if you have a negative 2 charge, you have to add 2 electrons to the total number of valence electrons. If you have a plus 3, you have to subtract 3 electrons from the total valence electrons. We will have some examples like this. Second step, draw a skeleton structure with the least electronegative atoms. Usually the first atom, but not hydrogen. Hydrogen can never be central atom in the center. Connect to outer atoms with 2 electrons. That basically it's a single bond. Third, distribute the remaining valence electrons on outer atoms or the surrounding atoms to form octet. For hydrogen, duet is good. You never have octet for hydrogen. 4. Place any remaining electrons on the central atoms if you still have some leftover electrons. Usually, you need follow the octet rule strictly for this 4 element: carbon, nitrogen, oxygen, and fluorine. Other element could have exception. 5. Make double bonds or single or triple bond if it's necessary. That means sometimes the central atom, if it's carbon and not octet, you need make double bond to make sure the central atom has 8 electrons. Number 6 is most actually very important. You have to minimize the formal charge separation. To calculate the formal charge, you need to use the valence electrons number minus lone pair electrons number minus bond number. So we will give you a lot of examples here. Before we give you the detailed example to draw the Lewis structure, we need to know how to find the valence electrons. If you draw the electron configuration of sodium, you will have 1s2, 2s2, 2p6, 3s1. If you use the noble gas shorthand notation, this core electrons can be written as neon. And this is the outermost electron, that's called a valence electron. Chlorine, same thing. You can draw this neon with 3s2, 3p5. The outermost layers or shells electrons is the valence electron. So for sodium, valence electrons number is 1. For chlorine, the valence electrons number is 7. Okay, so that's the valence electrons. And you don't have to go this way, so because in the periodic table of element, the group number give you the idea, the valence electrons number. For the 1A group, valence electron number is 1. For 2A group is 2. For 3A group is 3. 4A group is 4. 5A group is 5. 6A group is 6. 7A group is 7. 8A group is 8. So it's very, very straightforward. Okay. So keep that in mind, and then we will see the detailed example. Lewis structure of water. First step, we need to calculate the total valence electrons number of water. 2 times 1, 2 hydrogen. Each hydrogen, 1 valence electron. Oxygen, 6 valence electrons. So that's 8 together. And then we can draw the skeletal. This is a central atom, oxygen. Hydrogen is the surrounding. We put single bond between the central and the surrounding atom. Okay, for each surrounding atom, have a single bond. That uses 4 electrons. So we have total 8 electrons. Now use 4. We still have 4 left. That 4 electrons will stay on the oxygen, the central atom. And now if you double check it, oxygen octet, 8 electrons. Hydrogen duet. So that's actually a good Lewis structure for water. Okay, so that electron is the single bond Okay, two shared electrons is a single bond. That's another single bond. And that's lone pair electron. So oxygen has two lone pairs. Each lone pair will have two electrons. Now, formal charge calculation, this is the formula. Valence electrons number for oxygen is 6. There are 4 lone pairs electrons, 1, 2, 3, 4, minus 4, and there are 2 single bond, 2 bond, minus 2, so that's 0. Formal charge of oxygen is 0. Formal charge of hydrogen, 1 valence electrons minus 0. There's no lone pair on the nitrogen, and there's 1 bond, so minus 1, so it's 0. So that's perfect because that's minimized. So this has no formal charge separation. Perfect. This Lewis structure is good. For water, that's the Lewis structure. Okay, you can also draw that this way. So draw this two shared electron as a single bond, Sometimes you see this kind of Lewis structure, that's same. Look at the Lewis structure of ammonium. Ammonium is a positive charged cation. It's a polyatomic cation. And it's a positive 1 charge. So when you calculate total valence electrons number, you have to consider that you have the minus 1, subtract 1. So nitrogen's valence electrons number is 5. Hydrogen is 1, but you have 4 hydrogen, so 4 times 1. And you have to subtract 1. So then you have 8 as total valence electrons number. Then draw the skeletal structure. The central atom is nitrogen. Hydrogen is the surrounding. And then we draw single bond between central and each surrounding. Okay, that's 2 electrons. That's a single bond. That's another one. There are 4 single bonds. And then we actually already used all the available electrons because you have 8, used 8. That's 0. You don't have any left over. So look at it's nitrogen. It's octet. All hydrogen, they are all duet. So, and that's good. So formal charge separation, we calculate nitrogen, 5 as valence electron, minus no lone pairs, so 0, and there are 4 bonds, so minus 4 is plus 1. Formal charge of hydrogen, it's 1, valence electrons number, minus no lone pair, and 1 bond. That's 1 bond for each hydrogen. They all have 1 bond, so for each hydrogen, formal charge is 0. So that's actually minimum formal charge separation. And that Lewis structure need a bracket, shows the charge, and that's good Lewis structure. You can also draw this way. So draw the single bond like that. So that's also good. Don't forget the charge. Okay. Another example is a sulfur hexafluoride. We calculate total valence electrons number. Sulfur, valence electrons number 6. Fluorine 7, but you have a 6 fluorine, so total is 48. Now central atom is sulfur. You have a 6 valence surrounding fluorine, and draw the single bond between sulfur and the 6 fluorine. So 2 electrons, 2 electron, 2 electron. So total, that's 12 electrons we used. So we use 12, you have 36 left. Now 36 electrons will go to the surrounding because fluorine need an octet. So each fluorine need 6 more. So there are 6 fluorine, 6 times 6 is 36. So that's used all the left electrons, 36. Now you can look at this. Each fluorine, they are octet. Sulfur is not octet actually. Sulfur, there are 12 electrons. But it's okay, so because sulfur doesn't have to follow the octet rule. Okay, so if you calculate the formal charge for the sulfur, the 6 valence electron number minus no lone pair and a 6 bond 0. For each fluorine, that's 7 valence electrons minus 6 lone pairs electron. For each fluorine, look at the fluorine here. That's lone pair. There are 3 lone pairs. That's 6 lone pair electron and just 1 bond minus 1. That's 0. So that's also minimized formal charge separation. So that's good Lewis structure. Again, you can draw this way. So just a single bond between the central and the surrounding. You don't have to draw the lone pairs of fluorine. So usually people, this is good. Okay. Another example is xenon tetrafluoride. Calculate the valence electrons number. Xenon is the noble gas. Valence electrons number is 8, but you have a 4 fluorine, so total valence electrons is 36. Draw the skeletal structure. This is the central, 4 fluorine is the surrounding, and draw the 4 single bond between the central and the fluorine. So you have a 36. You use the 8 electron here. So 36 minus 8 is 28. You have a 28 left. For each fluorine, they need 6 more. So 4 times 6, 24. So you use 24 to fulfill the octet for the surrounding fluorine, but you still have 4 left. You use 24, you still have a 4 electron left. That goes to the central atom, xenon. So that it's lone pairs. You have 4 electrons will form 2 lone pairs. One lone pair, the other lone pair. Now you can say calculate the formal charge of xenon is 8 valence electrons number minus the lone pairs electrons is 4, and the bond, there are 4 bond, so minus 4, 0. The formal charge of fluorine is also 0. You calculate that. So that's good, right? Minimize the formal charge separation. And you can draw that this way. So you have 4 bond and 2 lone pairs of the central atom. Another example is a phosphorus pentafluoride, and lowest valence electrons number for phosphorus is 5, but you have a 5 fluorine. So 5 plus 5 times 7 is 40. Central atom is a phosphorus. You have 5 fluorine surrounding, and draw the single bond between them first, and you use 10 electrons. 40 minus 10 is 30. The 30 electrons will goes to the surrounding. Each fluorine needs 6 more, so 5 times 6, 30. Exactly use all the 30 electrons. All the fluorine now octet. So perfect. Now formal charge of the central atom calculate is 0. Formal charge of the fluorine is 0 also, so there's no formal charge separation. Another good Lewis structure. Again, you can draw this way, so just use a single line represent a single bond. Okay, look at this polyatomic anion, carbon dioxide. There's 2 negative charges. So when you calculate the valence electrons number, total available is carbon valence electrons number plus 3 times valence electrons number of oxygen plus 2, because it's 2 negative. For anion, you have to add the number of that charge as the valence electron. So total is 24. Central atom is carbon. So you have surrounding 3 oxygens. Single bond between them, and then you use a 6. 24 minus 6 is 18 electrons left over for oxygen. So each oxygen needs 6 more because they already have 2. So 6 more, 3 times 6 is 18. Perfect. Use all the electrons. Now you can go back to double check. Oxygen are all octet, but carbon only 6 electrons here. So you need 2 more electron be octet for the carbon. What you can do? You have to share 2 more electrons from one of the oxygen. For example, pick up this one. That 2 electrons will now be shared between the carbon and oxygen. Now for carbon, octet. This oxygen still octet. Octet, octet, oxygen. So that's good. And now you may notice that this carbon with this oxygen shared 4 electrons. So that's actually a double bond. So you can draw the formal charge. This carbon is 4 minus no lone pair, but you have 1, 2, 3, 4 bond. Double bond you can count as 2 bond. Actually, it is 1 is sigma bond, 1 is pi bond. So anyway, 4 minus 4 is 0. You can calculate the oxygen here. 6 valence electrons minus 4 valence electron lone pair, that's 2, minus 2 bond, 0. For this oxygen, 6 minus 6, but minus 1 is negative 1. Same thing, this oxygen is 6 minus 1, so negative 1. So that's a good Lewis structure for this carbonate. It's 2 minus, okay. And you actually can draw this way. So double bond, like I just said, okay. So, and you may ask, can this oxygen share that 2 electron instead of this oxygen? Yes, you can do that. So you can do this double bond here, or this oxygen you can have a double bond here. So these three Lewis structure, they are all correct. So we call them resonance. Okay. Another example of a resonance is a nitrate. It's a -1 charge, so you need to consider that when you calculate total valence electrons number. Nitrogen, 5 valence electron. Oxygen, 6, 3 oxygen, and +1 because it's -1 charge. 24 is total available valence electron. Central atom nitrogen, oxygen is the surrounding. Single bond between them, you use 6 electrons, so 18 electrons left. Each oxygen needs 6 more. 3 times 6, 18, perfect. You use all the 18 electrons left. Nitrogen, again, it's not happy, just 6 electrons. Oxygen, they are all octet. So you need share 2 more electrons from one of oxygen. Same idea with the carbonate. So now, the formal charge will be 0, +1, -1, -1. Okay, it's already minimized separation of formal charge. You have to use the bracket and negative. So that's a good one. You can draw this way. You can also draw double bond here or here. So they are also resonance because they are all good Lewis structure. And last example is a sulfate. Sulfate, there's 2 negative charge. So when you calculate the valence electrons total number, that's 6, that's a sulfur. Oxygen, also 6 valence electron, but you have 4 oxygen. +2, this is very important. So 32 is the total available valence electrons number. Central is a sulfur, you have 4 oxygen surrounding. Single bond between them, 1, 2, 3, 4. You use 8 electrons. So 24 electrons left. So that goes to the 4 oxygen. Each oxygen needs 6 more, so perfect. So that's all the electrons now. And seems like it's good, right? However, if you calculate the formal charge, okay, so yeah, don't forget the negative total charge. But if you calculate formal charge, you will see for this Lewis structure, sulfur will be 2+, each oxygen will be 1-. And so you actually can have another much better Lewis structure. Share 2 more electrons from this oxygen with sulfur, share 2 more electrons from this oxygen to the sulfur. Now, the sulfur will have 12 electrons. Not octet, but it's okay. Okay, so sulfur can have expanded more than 8 electrons. So now you can calculate formal charge. Sulfur will be 0. Sulfur 6 minus 6 bond, no lone pair, 0. See, oxygen 6 minus 2 lone pair, 2 bond, that's also 0. But these 2 oxygens still negative. But now this has much less separation formal charge than this Lewis structure. So this is the best. Okay, so that's why for sulfur, this is actually a correct Lewis structure. That's not good. Okay, so because less formal charge separation. Okay, so that's all I want to talk about the Lewis structure. If you have any questions, please make sure let me know. Okay, good luck.